Thomas Kindred from Wake Forest University with the talk Downstream Lessons from a Geometric Proof of Tait Flyping Conjecture. You are welcome.
Thank you for the introduction. Thank you for everyone for being here, and special thanks to all the organizers for putting together the conference. And it's a real honor to be included in this list of speakers. I'm excited for the opportunity. I'm going to be telling you about a proof that I put together a few years ago about Tait's Flyping conjecture, and kind of talking a little bit about how I think about Flyping, and showing some pictures of it. And then I'm also going to talk about some ideas that hopefully are at least a little bit related to the Flyping conjecture. Hopefully the story I tell is somewhat coherent. Hopefully it includes some interesting tidbits. It's going to jump around a little bit. All right, so Tait's conjectures date back to the end of the 19th century. They're about alternating knots and links in their diagrams. And there are three conjectures. The first is about crossing number. The second is about writhe. And the third is about all reduced alternating diagrams of a link. It says that they're all related by this single kind of move. And there's actually two different parts to the first Tait conjecture. One is that all reduced alternating diagrams of the same link have the same number of crossings. And the second part is that that's minimal among all diagrams of the link. And I'll come back to that point in a minute. Second conjecture is that all reduced alternating diagrams have the same writhe. And again, the third is that all of those diagrams are related by this single kind of move. These conjectures were extremely hard to prove. They remained unproven for almost 100 years. And shortly after the discovery of the Jones polynomial, there were several proofs that were announced. Tait's first conjecture was proven independently by Kaufman, Murasugi, and Thistlethwaite. And Thistlethwaite the nature of his proof is quite different than the other two. I believe it was Thistlethwaite and Murasugi who proved the second conjecture. And both of those, the first and second conjecture, were proven very quickly after the discovery of the Jones polynomial. It wasn't until 1991 that an announcement was made that the Flyping conjecture had been proven, and the paper appeared in the Annals in 1993. That proof is due to Manasco and Thistlethwaite. And all of these proofs use the Jones polynomial. And in their paper where they proved the Flyping conjecture, Manasco and Thistlethwaite observed this, that these problems had been open for a long time, and they'd now all been proven, all of them using the Jones polynomial, and they asked whether there were proofs that did not use the Jones polynomial. And the first such proof appeared in 2017 in a paper of Josh Green, where Josh Green answered a question that had been open since the 50s due to Ralph Fox. The question was, what is an alternating diagram? Sorry, what is an alternating link? In the sense of, can you describe what an alternating link is without reference to diagrams whatsoever? And I'll talk more about Green's answer to that question a little bit later. In the same year, by the way, Josh Howey also answered Fox's question, but in his paper where Green answered Fox's question, Green proved Tait's second conjecture and part of the first conjecture. He proved that all reduced alternating diagrams of a given link have the same number of crossings, and he proved that they also have the same writhe. Okay, so a few years later, I announced this proof of the Flyping conjecture, and it builds on Josh Green's work. And I'm going to start by saying the main idea. And the main idea is that we're going to leave the world of reduced alternating diagrams, and we're going to, instead of thinking about diagrams, we're going to think about pairs of surfaces. And these two surfaces are going to be the checkerboard surfaces from a reduced alternating diagram, except they're going to be not in reference to the diagram. Instead, they're going to have some extra properties. We're going to assume that they're incompressible and boundary incompressible. And we're going to assume that there's something called positive definite, negative definite. One is F pluses. One of them is each. And later in the talk, I'll tell you what that means. Right now, it doesn't particularly matter. And Green, this correspondence is almost entirely due to Green, although there's something in the uniqueness part that, strictly speaking, is due to myself. And under this correspondence between diagrams, which are the thing we're trying to prove something about, and surfaces, which is how we're going to prove it and understand it, the flight moves on the diagrams correspond to certain replumbing moves on, and each flight move is going to be a replumbing move on one of the two checkerboard surfaces. So there's going to be a dark surface or a black surface, and there's going to be a white surface. And this sequence of pictures down here is this first picture is a replumbing move. It's replacing this green disk in the dark surface with another disk. The second disk is harder to see. It's comprised of a yellow disk that's above the projection, the horizontal plane here, and a blue disk that's kind of the same on the opposite side. And they're glued together, those two disks, along an arc right here. And then if you flipe, so these two diagrams are the same. If you flipe the diagram, then this actually flattens out the yellow and blue discs right here. And so the insight is that from this first picture to this last one, it's an isotopy of the white surface, and it's this replumbing of the checkerboard surface. Now, this is kind of a hard picture to see. And so the first thing I really want to do with my talk is give you some more pictures to give you more of a perspective on these replumbing moves and what they have to do with flyping. So here's the 6-3 knot, and the 6-3 knot has an advantage that it's amphichiral, and so whatever I end up saying about the black surface, kind of the same thing is going to be true with of the white surface, except it'll be the mirror image. The 6-3 knot also is a true bridge knot, which means that all of its spanning surfaces have this nice structure described by Hatcher and Thurston in a 1985 paper. And this black surface over here breaks down as 3 bands plumbed together. The first band is an annulus with 2 half twists. The second one is a Mobius band with 3 half twists. The third one is a Mobius band with 3 half twists. And we plumb these two together by gluing them along these green squares. You can see the glued together square there. And likewise, we glue these together along that square. We can draw the same surface as a checkerboard surface. This is the picture. We can see the green squares here. Now, the thing that's harder about this picture is that here the squares are twisted, but they still have 4 edges. And we can also see these building blocks drawn as checkerboard surfaces. And for example, this annulus and this Mobius band get glued together along this green square. That happens right here. This is the green square. This is the green square. They get glued together. That's the green square where they get glued together. And by symmetry, the exact same thing is true, except as a mirror image and maybe turned upside down for the white surface. And I've drawn it here at the bottom. Okay, so all I've told you so far in this picture is we've got 2 checkerboard surfaces. We can think of the surfaces as plumbings of annuli and Mobius bands. But if you're familiar with this paper of Hatcher and Thurston, they also describe how there are other spanning surfaces that are supported by kind of the same pattern of 2-3-3. And the way that those surfaces are related to the one that I've drawn here is by replumbing. And you may have seen a picture like this of, let's take this square here and let's replace it with the outside square. And this is a replumbing move. And it's the exact same replumbing move that I'm talking about. And here's another picture of the same surface, one which is harder to see. But I do want to spend a minute on this slide, giving you a chance to look at it. What's going on here is this outside disk that's filled in this picture is now right here. There's 2 parts of the disk, and there's a red half on the near side of the projection plane. Its boundary is this red arc that you can see, and then a purple arc that's in the unshaded region. And then there's also a blue arc on the far side of the projection plane, a blue disk on the far side of the projection plane. You can kind of see where it's shaded blue. The boundary of the blue disk is the same purple arc. And then there's a blue arc, which is harder to see. It's kind of a dotted arc. I'll zoom in closer. And the red disk and the blue disk get glued together along the purple arc to make a disk. And that one glued together disk, its boundary is red arc union blue arc. And that red arc union that blue arc are the boundary of this green square that we removed. So this is a replumbing move. Replumbing move is you replace a disk in the surface with a disk outside the surface that has the same boundary. And again, There's some nice symmetry to this example. And so just as we can replumb this surface by replacing that square with this funny looking one, we can replace this square with that funny looking one. And by the way, in Hatcher-Thurston's paper, they say most of the time when you replace these inner squares with outer squares, the surface that you get is not isotopic to the original one. And they say precisely when it is and when it isn't. And again, it's almost always different. The one exception is anytime you've got a Hopf band, you can always kind of do some sort of local monodromy. I'm kind of thinking of the Hopf band fibering 3 space. And so actually, it turns out that if I replace this one with the outside one, that wouldn't change the isotopy class. And so I've kind of done the only interesting thing I can do in this example to each surface is I've replumbed it in the one distinct way that's possible. Okay, so on the previous slide, I explained how pairs of surfaces are going to describe diagrams. So here's a diagram. And the pair of surfaces is, let's say, this one and this one, right? Those are the black and that's the black surface, that's the white surface. But then here's another surface that's related to that one. It has all the properties it needs to. And here's another surface that's related to that one. And so you can ask, well, all right, under this kind of, under this perspective of pairs of surfaces correspond to diagrams, what does that look like? So that's what's happening on the next slide. So here, this is the diagram that we started off with. And this is the black surface. This is the white surface. And we've done these replumbing moves to get this version of the black surface and this version of the white surface. And it's going to turn out that this is the diagram that they describe. And I think one thing that I found interesting to take away from the geometric proof is that the sequence of flight moves that's going to go from here to here, well, there's only 2 of them, right? There's only 2 replumbing moves. I could do the black surface. I could replumb the black surface, then I could replumb the white surface, or vice versa. But in fact, in general, the black surface might require several replumbing moves, and you can always do all of your replumbing moves of the black surface, and then all of your replumbing moves of the white surface. And so I find it useful to use this notation. This notation will be, this is the diagram determined by the surfaces B and W here. This is the diagram determined by the surfaces B prime and W prime. And so there are going to be 2 options for an in-between surface for what we get if we replumb one but keep the other. And here they are. So if we replumb the black surface but keep the white one, this is the diagram we get. If we replumb the white one but keep the black one, this is the one we get. And the last thing I want to say about this slide is, what are the red and blue circles? So the red and blue circles are corresponding to both replumbing moves, and they're also corresponding to flips. And so here, this red circle corresponds to this. It's the circle that goes through this. No. Did I turn my picture upside down? That's going to make it harder to explain, isn't it? I'm gonna draw on top of the picture. Will be a better option. All right. So there's one of these green squares that passes right through here. And so somehow this red circle is describing the replumbing move associated to that green square. But then also there's a Flyping move, and the Flyping move involves this crossing. And so I want to draw this. Yeah, I'll draw it. Okay, so here's the replumbing move. There's that red crossing that's circled, and there's going to be a bygone inside here. And I want to take this bit and I want to kind of drag it around like this. So I'm kind of redrawing just those ends like this. And then you do a flyp, and the flyp moves this crossing to the bottom of the tangle. As you can see, the crossing is at the bottom of the tangle here. And so this kind of circle that passes, this is going to be called a Flyping circle. And what characterizes a Flyping circle is that it hits the knot in 3 points, one of which is a crossing point. And it's both where a flight is possible and also where this kind of replumbing move on one of the checkerboard surfaces is possible. All right, so this is kind of the big idea of the proof without really any details of how the actual proof happens. And this is where I'm going to kind of go off into some digressions about things that are related to what I was just talking about, of pairs of spanning surfaces determining diagrams, replumbing moves, and so on. So the first thing is that this correspondence between pairs of checkerboard surfaces from alternating diagrams and alternating diagrams, this is very much depending on the fact that we have an alternating diagram. And so in general, if you have two spanning surfaces for the same knot, it's really not reasonable to hope that there's going to be a diagram whose checkerboard surfaces are isotopic to your chosen pair of surfaces. And this is kind of the simplest example I can cook up. These are two spanning surfaces for the unknot. One of them is a disk. And if you think of the diagrams for the unknot whose that have one of their checkerboard surfaces as a disk, in fact, you can characterize them by they're all related to the trivial diagram by a sequence of Reidemeister 1 moves. And all right, something like this. Maybe it's more convincing if I go like that. Okay, so one of the checkerboard surfaces there is a disk, and you can't do anything more interesting than that. But the thing is then, if one of your checkerboard surfaces is a disk, then that means that the complementary checkerboard surface is always going to contain a Mobius band, right? Because your last Reidemeister 1 move that you did, here's a Mobius band, here's the core of a Mobius band. Well, this surface doesn't contain a Mobius band, therefore it can't be the complementary checkerboard surface to this one. Okay, so that's kind of a silly example. I wanted to come up with another example, and wanting to minimize the effort that went in, and also kind of wanting to minimize the number of times I had to get lucky in the problem, I decided to choose a diagram that had lots of symmetry. And so the diagram I chose was this one, this diagram of the 3-4 torus knot. And what makes this diagram particularly nice is actually not its rotation symmetry. What makes it really nice for the purposes here is that the two checkerboard surfaces for this diagram are actually isotopic to each other because of the symmetry of the diagram. And then if you take either one of those checkerboard surfaces, and you can say something interesting about it, then maybe you have to work half as hard. So here's another diagram of the 3-4 torus knot. And what you can do, and I'm not going to go into the details, is if you take these, you can find a pair of boundary compression moves. And the boundary compression moves give this surface right here, except without these two kinks in it. And so that means that the original surfaces are isotopic because of the nature of the boundary compressions that end up being performed to this surface right here. And so it's surprising that both checkerboard surfaces for this are isotopic to this one. Same thing is true for this diagram, but they're obviously different diagrams. And so a given pair of diagrams does not uniquely determine, a given pair of checkerboard surfaces does not uniquely determine a diagram, even in the rare cases where it does determine a diagram at all. There are plenty of natural and interesting questions I think you could ask here of, given two surfaces, spanning surfaces for the same knot, is there a way to tell whether or not they're checkerboard surfaces for a diagram? You could certainly find obstructions, but is there a systematic way to do it? As far as I can tell, this is completely wide open. Okay. Now I want to get back toward telling you what a definite surface is. Definite surface, I'm going to explain it first by saying what a Goerritz matrix is. A Goerritz matrix is you take a knot diagram, you look at a checkerboard surface, and this checkerboard surface has a natural basis for its first homology, consisting of circles that go around the unshaded but bounded regions of the diagram. And Then you count how many half twists there are in each of those circles going around those holes. Those are your diagonal entries. And you count how many times each circle interacts with the other one. You count them somehow with sign. Those are the off-diagonal entries. You can see here that the green and the blue and the purple interact. So that's why there's a non-zero off-diagonal entry, as do the red and the purple. But the purple and the red don't interact. So that's why this off-diagonal entry is a 0. And this matrix actually is describing something. It's describing how actually any circle in the surface is framed. So given any circle, you can find a vector that represents it in terms of this homology basis. And then this matrix describes some sort of deformed inner product. And if you apply that inner product to this vector with itself, that tells you double the framing of the curve in the surface. Now, there's something more general going on here, which is that any spanning surface, whether or not it's checkerboard surface, has a pairing on its first homology group. It's a symmetric bilinear pairing, first described by Gordon and Litherland. And the way that you define it carefully in general is you take a double push off of one of your curves. You can define this using the transfer map on first homology, or you can use a picture. The picture is, here's your curve. You're going to push it off in both directions. So the green right here is a slice of my original surface F. And then I'm going to thicken the surface F up and take the boundary of that. And so then there's kind of 2 copies of the surface locally. Although if the surface is orientable, there will actually be 2 exact copies of the surface, one pushed up, one pushed down. But if the surface originally is non-orientable, the blue surface will be connected. In any case, if you have a curve down in your surface, you can lift it to a double in the doubled surface. And that curve represents tau beta. And importantly, this one lives on the doubled surface. This one lives on the original surface. The doubled surface and the original surface are disjoint. So you can do a linking number. It's not a priori, it's not obvious that this is symmetric, but Gordon and Litherland prove it. And so this pairing exists on any spanning surface, and this matrix represents that pairing with respect to this basis. And then what it means for a surface to be positive definite or negative definite is that this pairing is positive definite or negative definite, meaning that any homology class other than 0 paired with itself always gives you a positive number. That's what positive definite means for the surface. And what that means, at least in the case that you have a spanning surface for a knot, is that every circle in the surface has positive framing unless it's null homologous. Okay, and then Green proves, this is Green's theorem, that a knot in 3 space is alternating if and only if it has a positive definite surface and a negative definite surface. And moreover, if you have such a pair of surfaces, then there's always a diagram whose checkerboard surfaces are isotopic rel boundary to the positive definite and negative definite surface that you have. This is actually, Josh Green proves something more general. First of all, this works for links and not just knots. In general in the talk, I'm saying knot rather than link because there's often a caveat for links, and this will just make things a little bit easier. And also Josh Green's theorem works for rational homology spheres in general. And the conclusion in that case is actually, if you're in a rational homology sphere and all this stuff happens, that actually you're in 3 space. And so partial intuition for the easier half of the theorem. So why are the checkerboard surfaces from an alternating diagram positive definite and negative definite? Well, if you have any simple closed curve, or in fact any homology class, but let's say just any simple closed curve. No, if you have any homology class in your surface, you can always find a representative that every crossing that it passes through, it only passes through that crossing in one direction. And so if you went opposite directions through a crossing, you could do some move that reduced the number of times your curve or multi-curve intersects that crossing until every crossing looks like one of these pictures. And then you can look at the local contribution to the framing of your curve, and it turns out to be 1/2 times the square of the number of times that the curve passes through the crossing. And since all of the crossings then have non-negative contribution, and your curve is non-homologous, so non-null homologous, so it has to pass through at least one crossing. It has to have positive framing. And the reason I mention this is because, well, look, everything's twisting in a positive way. That's why it's positive definite. That's why right? That's the intuition. And based on that intuition, I really thought that if you took the doubled surface of a checkerboard surface for reduced alternating diagram, that the same thing would be true. That, let's take this picture and let's thicken it up a little bit. It's still true that everything twists locally here in a positive way. And so I really thought, and by the way, you can do the same construction that Gordon Litherland described of you take your doubled surface, you can double it again. And so you get this, so you can get a symmetric bilinear pairing that's measuring the framing of any curve on your surface. And based on this intuition, come on, everything's got to have positive framing, right? I mean, everywhere it twists, it's positive framing. And it turns out that's not necessarily true. And the reason is that once you go to the doubled surface, now you don't have to have an embedded surface in the spanning surface. You can have a surface that crosses itself in the spanning surface on opposite sides. And so that's what's happening in this picture is, I've got a curve that's passing on the near side of the spanning surface, and then it does something over here, and then it comes back, and then it passes on the far side of the spanning surface. And you can, and this has some local negative contribution, which I believe is -2. And you can use this to cook up an example in the following way. So I had some beautiful picture of this somewhere, and I looked for hours, and I couldn't find it. And it would be awful if I didn't spend many more hours drawing it. So I'm going to just describe the idea of the picture. Is you take a boundary connect sum of a bunch of 3 half-twist Mobius bands. And maybe at the end, you also throw on a 2 half-twist and Hopf band, right? But here's a Mobius band with 3 half-twists. Here's another one. The ... means we have a bunch of more in between. We have some more over here. And then what you can do is you can have a curve that passes over every single one of these bands. And it really feels at this point that you completely have something that has positive framing. And at this point, that's kind of all that it is. But you can construct this surface in such a way that in this disk right here, it passes over itself a bunch of times. So it's passing over itself on the front. And let me do something less comically huge on the back. And if you're careful about your orientations, you get enough of these crossings between the front and the back that that the negative contributions from this thing passing over itself outweigh the positive contributions of going over the bands, and you can make something that has arbitrarily large negative framing on the double of the surface. Okay, so this was surprising to me when I found it. It also felt like, okay, you have to have several bands. This seems like, kind of a contrived example. This must be an exception. But then I had a master's student and co-advised with Hugh Howards and Frank Moore. And the student, John Tolbert, actually found that there's a way simpler way to do this. And in fact, almost every alternating knot or link, maybe the only exceptions are 2Q torus knots. Maybe you have to carve out a few more exceptions than that, but you don't need very complicated examples. There's a very simple construction that gives you these at least 0 framed or negatively framed, but this construction is 0 framed curves on the doubled surface. But the thing is that this curve that we end up constructing in this example, and all of the curves that we construct here, all end up being knotted curves in the surface. And so it remains an open question of whether there's an unknotted simple closed curve on the doubled surface with 0 framing or negative framing. And the question with 0 framing has extra relevance considering the following context. So suppose that you have a checkerboard surface from an alternating diagram, and it has an unknotted simple closed curve with 0 framing. Well, then that means that there's a disk in 3 space whose boundary is that curve, and near the boundary, because it's 0 framed, near the curve, the disk is disjoint from your surface, which means that the disk is going to intersect your surface, your spanning surface, in some collection of arcs. which would then mean if you cut your checkerboard surface along those arcs, you'd get something that was pi1 non-injective. Now, it might still be geometrically incompressible. In fact, it's guaranteed to be geometrically incompressible because it's still going to be a positive definite surface. But I don't know. For my money, I would be really surprised if it was possible to take a checkerboard surface from an alternating diagram and cut it in some way and end up with a surface that's not pi1 injective. But in order to prove that that's impossible, I'd like to prove that these zero frame curves are always knotted, and I kind of have no idea how to do that. Okay, like I said, digressions on digressions. Another thing, this is kind of just like, I want people to know this, that I was talking about Gurit's matrix. Gurit's matrix represents a Gordon-Litherland pairing. I kind of thought it was semantics of one's a matrix, the other one's the pairing, but there's actually a very, very important difference that a Gurit's matrix actually in the literature is specifically a matrix that arises by the construction I described earlier. If you take a checkerboard surface and you choose your homology basis to go around the unshaded regions. And that's the definition of a Gurit's matrix. And in particular, you're not actually allowed to do just whatever change of basis you want to do on a Gurit's matrix. It's not necessarily a Gurit's matrix anymore. And based on this specific definition of Gurit's matrix, which is traditional, Traldi proved in a pair of papers that were pretty recent, I think they were maybe 17 and 19 or roundabout there, that the condition of two knots, and I believe this also works for links, having the same Gurit's matrices is exactly the same condition as the knots being mutants of one another. And then what this means is that we've got all of these knot invariants that can't tell mutants apart, and Traldi deduces from this correspondence that actually all of those invariants, including the Homfley polynomial and the Jones polynomial, are in some way completely determined by a Gurit's matrix. And then Joe Boninger more recently worked this out explicitly for the Jones polynomial. Joe described, given a Gurit's matrix, how to determine the Jones polynomial from it. Well, I kind of took a while to get to realize this. And so in the meantime, I've been thinking some about Gordon-Litherland pairings. And so a few years ago, for the encyclopedia, the Concise Encyclopedia, I proved this theorem, that all checkerboard surfaces for all diagrams of a given knot are related by isotopy and these simple moves that I now call kinking and unkinking because that's what my student decided to call them. This is closely related to a classical theorem that says all Seifert surfaces for an oriented link are tube equivalent, and another theorem proven by Gordon and Litherland. That one was first proven by Levine, but also the best proof is due to Kaufman, Barnaton, and Fullman, the one about tube equivalence. And then there's a theorem due to Gordon and Litherland that says all spanning surfaces for a given knot or link are related by these moves here together with tubing moves. And so, anyway, so my proof of this is very similar to those proofs, but it has some implications for the matrices that represent Gordon-Litherland pairings, which is that all Gordon-Litherland matrices, as I'll call them from now on, at least for all checkerboard surfaces for a given knot, are related by change of basis and by the move that corresponds to this, which is just you add a +1 in the bottom corner, you add a -1 in the bottom corner, or you remove that. Okay, the top half of this slide is what I already just said. And so something strange happens here, which is that, okay, so the point is that, yes, Gurit's matrices determine a Jones polynomial. Very important subtlety that I just realized recently and I want to share with you all is this is not true of Gordon-Litherland matrices. And here's a very simple example of the 5-1 knot, also known as the 5-2 torus knot. This is a spanning surface. This is its Gurit's matrix. If you add a negative kink to it, this is the Gurit. This is also a Gurit's matrix for a different surface. If we start from the other end of this line, this is the mirror image. It has this Goertz matrix. You add a positive kink. And then the surprising thing, it's not too hard to do, but it's also not that interesting, so I left the details out, is that these two matrices are related by a change of basis. And also, these two surfaces, these two knots have different Jones polynomials. And so, well, it can't possibly be the case that, so what I want to say is, this is a Gordon-Litherland matrix for both knots, but it can't possibly be a Goertz matrix for both knots because the knots have different Jones polynomials. And so the point is that this change of basis is somehow at this place in between. Goertz matrices are much more rigid thing than Gordon-Litherland matrices, and the rigidity comes in of you're just not allowed to change basis in the world of Goertz matrix. Okay. All right. I'm getting low on time, so maybe I'll skip this other. There's some other idea I have about how Gordon-Litherland matrices versus Goertz matrices could be interesting. One possible reason it could be interesting is Tait's first conjecture about reduced alternating diagrams minimizing crossings still has no geometric proof. And so there's every diagram has a Kaufman state with a single circle. There's some matrix that you can get from that as a Gordon-Litherland matrix that might have some relevance to this. But let's see, is there something else that I want to say? Gosh, in 3 minutes, am I really going to try to tell this story? Well, there's a geometric proof. What do? You take your surfaces. You've got a diagram that you know and some other diagram, and you want to find a sequence of Flypes, or at least know that there's a sequence of Flypes between them. And so what you do is you look at how one of your surfaces sits relative to the surfaces from the other diagram, and you play some game. And this game involves Monasco's crossing balls. You do something where if there are crossing bands, you make some assumption that your surface is always on a certain side of your projection plane nearby. This introduces some sort of asymmetry. And now you do a bunch of moves. All right. And these moves you do according to some hierarchy. So you do whatever move one is, you do it if it's possible. If move one isn't possible, you do move two, and so on. And you work your way through these moves. These are all isotopy moves on the surface. And the details really aren't important. What I do want to say is you can, this is like a hierarchy of moves that you see in classical 3 manifolds. There are a few cases where this kind of technique has been used. And it's useful in a few ways. So one is you have some notion of complexity associated with this hierarchy of moves, and you make some complexity argument that the sequence of moves has to terminate. And then you argue that when it does, something nice happens. But the best part, after you argue that it terminates and that something nice happens when it does, is then you get to put the whole thing in rewind. And the fact that your moves were organized in terms of some hierarchy allows you to actually say, the very last thing that happened, you can really put some restrictions on that. And so there's this intermediate theorem in the geometric proof that says that when you do these isotopy moves 1 through 9, then the surface you're looking at, the way that it intersects basically the projection sphere, is a collection of circles. And for free, what ends up happening is that every one of those circles describes a Flype. And so I want to conclude with this slide. So on this slide, we've got some, on the top left, this is the kind of picture that might result from after this hierarchy of moves 1 through 9, is the red, purple, and blue are, well, the red and the blue are the boundary of some other surface, and the purple is how that surface is intersecting the checkerboard surfaces of the diagram that we're looking at. And you can notice that there are 4 circles here. And each one of these 4 circles does kind of the right thing for a Flyping circle, namely it goes through one crossing and it hits the knot 2 other times. Again, goes through one crossing and hits the knot 2 other times. And something else you can notice here is there's like some arc on the boundary of the surface that you really could get rid of, but these moves have been designed in a way that actually I'd rather have that arc here because this circle is so nice. It describes a flype, and so does this one. And if you perform those 4 flypes, then afterward, then the surface you're looking at is isotopic to your given black surface. And so what this means is that actually, given any diagram, given any pair of diagrams, you can see the black surface and you can see the white surface all at once in your. So if this is diagram 2, and this is diagram 1, we can see all of the flypes to go from 1 to 2 in diagram 1, and what they represent is how the black surface from diagram 2 intersects everything in diagram 1. And you can do the exact same thing actually for the white surface. And so you can get a collection of circles in this just by doing isotopy that all at once encodes the entire sequence of flypes. And you can then from that, you can get, for example, a bound on the number of flypes between diagrams. But since I'm past time, I will go to my thank you slide. Thank you.
Okay.
Happy birthday, Luke.
Mhm.